Today's solid-state quantum computers are facing one major issue in scaling, which is how do you make sure that you get all the signal down to your chip without coupling too much energy. So basically the number of lines that are going down this chandelier type of architecture into your cryostats that are for the signal processing as well as for the reading and signal control types of applications. So this is the major bottleneck in today's type of quantum computing architecture when it comes to solid state. And today we are looking at SEEQC, a company that is trying to solve this by moving all the control electronics down into the cryostat, into millikelvin stages. And if you are interested about that, and if you want to learn more about this company and how they're actually doing that, then join me for today's episode of the Hidden Quantum Champions. And with that, let's get right into it. But before we do so, as per usual, make sure to get yourself something to drink. This might take a couple of minutes, this episode. And then also, if you don't want to miss out on the next one that I'm going to show you, make sure to subscribe already to the channel right now. So here we are on their website. It says SEEQC. I hope I said it correctly. And it says quantum computing on a chip, the processor platform for the next computing era. And here we see the chip, or I guess a mock-up of what this chip would look like, with some cool animations as we scroll down. And then here we see, the chip getting integrated. It's called FC3, SFQ plus FFC. And here it says making quantum computing scalable. So SEEQC is the first company to put all core functions of a quantum computer on a digital chip, unlocking a clear path to scaling qubits without scaling complexity. It's the architecture that makes practical large-scale quantum data centers possible. And then of course you see here the chips which are sitting on some system. Disclaimer on this point, I don't think that they are building a technology where you can put like a chip into your smartphone and suddenly your smartphone becomes a quantum computer or your laptop becomes a quantum computer. I think we are still talking about, let's say, low temperature setups, cryostats, things like this. So basically still large apparatus, because controlling a quantum system requires to be able to not have any temperature disturbances, and for that reason you need these type of cryostat setups. But still, I mean, the idea is to kind of move into a chip. And let's move down here. So there's some major publication here from March 2026. I'm recording this in April 2026 from Nature Electronics that says superconducting electronics for superconducting qubits. And then a quantum computer controlled by superconducting digital electronics at millikelvin temperature. And there's a link to the press release as well as the full article and some video down here as well. So the electronics that they are envisioning to use to control let's say the chips, so the digital electronics, which is still relying on standards ones and zeros, is built upon superconducting technology. So it's a superconducting digital electronic circuit. And then in addition to that, you would have the, let's say, quantum computing type of circuit using the classical, probably as well, superconducting technologies like Josephson junctions that we know about. So let's see if we can learn a little bit more about how that works. So SEEQC integrates all core functions of a quantum computer on a digital chip at the same temperature as the qubits. The result is a 1 billion x improvement in energy efficiency and a clear path to scaling up qubits without scaling up complexity. Full stack quantum system on a chip, all core functions on a single cryogenic chip. And then here we see digital integration and quantum AI with NVIDIA QPUs. So SEEQC's digital chips integrate seamlessly with NVIDIA GPUs for quantum AI and heterogeneous compute. Billion-fold energy efficiency, so dramatically lower power per qubit from 3 watts to 3 nanowatts. And I guess the 3 watts, they are calculated as what you usually need to control those qubits, as in like signal processors, signal generators that kind of then move your signal down into the cryostat, various filter stages in between that kind of reduce the amplitude of the signal, but at the same time also dissipate heat. And probably this in average generates 3 watts versus the 3 nanowatts, which is probably the signal generation down on the chip and only the digital interface to, let's say, the higher temperature side of things. It also increases the speed and the latency. So it says 10 times faster and 10 times lower latency, rapid on-chip readout, and feedback loops for error correction. So we see that the signal processing is really supposed to happen on the chip itself. So the readout is happening on the chip, maybe not the signal generation, at least it doesn't say that here. And then there are feedback loops for error correction implemented on the chip as well. Any qubit, any application, so compatible with all qubit types and use cases. So that means we are not only talking about superconducting qubits here, we are also talking about other technologies that can be implemented on chips, like for example spin qubits that can also be implemented in a very similar way, and maybe also in the future Majorana types of qubits, depending on the way that those are being implemented on a chip basis. And here we see the qubit module, and then on the side we see these SEEQC chips that are basically surrounding it and then probably serve as signal generators. So here's a link to how it works. At the core, SEEQC is the world's first digital quantum computing platform built on superconducting chips that combine qubits and classical logic in a single cryogenic system. Here you can explore the details from technical specs to published research, and we are not going to look into this for now. We move down a little bit because there's also a white paper link down here that explores why scaling, not just building the first quantum computer, will determine who leads the next era of technology, from accelerating drug discovery and clean energy to securing communications and transforming AI. SEEQC outlines the breakthroughs, risks, and policy actions that will define the future. And then there's a link to the paper here. As per usual, we see that there are partners in the ecosystem as well. So we see Rigetti, NVIDIA we've seen before, IQM, BASF, and Merck as potential, applicants or users of this technology, and many other labels here as well, like the US Department of Defense and then universities and so on. There are also some news articles linked down here, and as per usual, the call to join the team and some information about SEEQC, which was founded in 2019, but we will look more at the company in a later stage of this video. Now let's quickly explore the technology. So we have talked about it already a little bit, right? So it is about implementing digital electronics on the low temperature stage. And I mean, if that really works in a scalable way, I think it is something very interesting. Already when I was still in the research lab and working with this low temperature stuff, we were facing the issue that with every upgrade of chip complexity, of signal generation and readout, we had to scale the cryostats. So at the very beginning, the cryostats were small and they were getting bigger and bigger. And with that, of course, the requirements for cooling, they grow at least linearly to the number of lines that you want to draw down. And I mean, that works fine if you want to drive, let's say, a couple of tens of qubits, but not for millions of them. So that's where you reach some limitations, right? And already there, the idea was, can we move the electronics down into the cryostat to reduce the number of lines that we have to draw all the way down to the stages where the cooling power is very, very small only. And I mean, this is basically at the extreme what SEEQC is looking at right here. So they basically say the electronics should go down to the lowest stage, which is the millikelvin stage. At least in the previous page, I think they said that. There are, of course, also other stages like the 1 Kelvin stage and the 4 Kelvin stage, and let's say the liquid nitrogen stage. And maybe these ones could also be interesting to consider for these types of electronics. So maybe we should think about it in a staged way, where we have different stages that can host different stages of the signal processing and readout. But here it focuses on an on-chip solution, which is all the way down to the lowest level. Of course, building something like that based upon superconductors is not really easy, because at, let's say, room temperature, we have this great thing called transistor, which we can tune like a little switch. It can be turned on and off by applying a voltage to the gate. And I mean, the transistor technology is really what drives all of today's electronics. But if you think about the cryostat, it operates at very low temperatures, and there the semiconductor, which is the material that is being used to build a transistor, is not working as it is at room temperature anymore. So you need to have much more dopants, because these dopants, they are needed to create the electronic flow across the semiconductor, because a plain semiconductor, like if you just have silicon, it's basically not a conductor, it's an insulator with a narrow band gap. And then if you introduce those dopants, which is basically like mixing dirt into your pure silicon crystals, or bringing other atoms in, then you can basically donor. So there's donors that can basically donor electrons into the silicon crystal. But technically, if you cool down the system, those electrons again get stuck at the atoms that have been introduced, these impurities, and therefore it becomes again not conductive anymore. And that's why you need much more of those if you reduce the temperature. That's, by the way, also why they work very well as temperature sensors, so semiconductor temperature sensors. But then ultimately, if you go down to the lowest temperature stage, you will not be able to run any currents anymore through those semiconductors, because all the, let's say, charge carriers, they are frozen, they are stuck with their donoring atoms again. So they are not donated anymore to the silicon crystal, and therefore you cannot basically build with a standard semiconductor a chip that can operate at these very low temperatures. And that's why you need to come up with something else, and that's probably the idea behind this superconductor based technology. Now, in order to build something like this, you basically need to be able to, let's say, replace the transistor with some superconducting element. I'm not really sure how this is done. Probably there will be some information available on the, let's say, scientific resources, but let's jump into the technology here and see if we can learn something about that already from the website. So it says the world's first quantum computer on a chip, SEEQC, system on a chip approach, integrates classical single flux quantum SFQ logic with quantum circuits on the same cryogenic platform. By implementing miles of cabling, by eliminating miles of cabling and reducing latency, our architecture makes quantum scalable and energy efficient. So, single flux quantum logic. Logic, I mean, we know that. This is this 1 and 0 logic that we know from classical system. Single flux quantum, what is this? So flux relates to the magnetic flux. It's a property, a magnetic property. So if you think about the Earth, it has a magnetic field, and you can measure that with a compass, right? It points along a specific line. It connects basically both of the poles of the Earth. So you have the North Pole and the South Pole, and the magnetic field is running like a loop between those. And that's basically what you see when you pull out your compass, or your phone, because there's a compass in it. It will always point along these lines. So you can easily see where North and where the South Pole basically are. Now, this magnetic field is also in a way a quantum property, and there's a quantization of it. So there's the smallest possible unit of the magnetic field, and that's what we call a single flux quantum. So if you take a very tiny loop, like a superconducting loop, and you introduce a current into it, so a current is running through this loop, then it will create a flux. So there's going to be a magnetic field that is evolving through this loop, very similar to when you take a coil, like a copper coil, and you draw a current through it, then you create a magnetic field. That's how electromagnets work, right? And if you do that at the smallest possible limit, you can create these fluxes. And there can be, let's say, a flux that is pointing in one direction, a flux that is pointing in the other direction. And I assume this is basically how this is implemented. Very similar, maybe like the magnetic implementation, similar to the whole field of spintronics that has been developed previously and has been worked on a lot. So if you're interested in spintronics, let me know down in the comments below. I can do also a little session on that. I know a little bit about it. So, okay, and I guess that's where it starts here. So you're using the single flux quantum as a basically logical unit, and then you're operating on that. You can read it out, you can manipulate it, you can probably run gates on it, and that's how you do your logic part. So here it says the biggest challenge to quantum computing is scaling. SEEQC's integrated digital chips are the solution. No matter the qubit modality or the role in the quantum ecosystem, everyone is faced with the same challenge of scaling. By integrating room temperature control functions and classical single flux quantum SFQ logic with quantum circuits and placing it side by side with the qubit inside the same cryogenic platform, SEEQC's architecture makes quantum scalable and energy efficient. By placing control on a digital chip together with the qubit, we have created the world's first integrated quantum processor chip, increasing speed, latency, and fidelity while using less energy, lowering cost, and getting rid of cables and complexity. Here's basically the conventional system, and that's what I mentioned before, right? You have all these control lines that are basically going down in the cryostat, and the whole control of the qubit is happening outside at room temperature with these racks. And the more qubits you need, the more of those racks you need to actually do the whole processing. So yeah, quantum computer, and then analog logic, and then analog to digital processing, and then the digital link, and then here's the whole processing, digital data center. And that's basically the QPU setup that we are seeing now in the first prototypes also with supercomputers. So redefining architecture, quantum on chip, we place the control system at the same 20 millikelvin stage as the qubits using SFQ, so single flux quantum digital pulses. Quantum architecture simplified, so SEEQC's quantum computing system on chip integrates classical single flux quantum logic with quantum circuits on the same cryogenic platform. By placing the control electronics at the same temperature stage as the qubits, SEEQC eliminates bulky cabling, reduces noise, and dramatically improves performance. This architecture makes quantum operations faster, more energy efficient, and scalable for real-world application. Key outcomes, so ultra-low latency, we've talked about that before, reduced error/noise, because you're operating at those lower temperatures, you're not prone anymore to the temperature noise that is just created on the electronics because of temperature and the statistics that comes along with temperature. Energy efficiency, and then scalable integration. We place the control system at the same 20 millikelvin stage as the qubits using SFQ digital pulses. This eliminates cabling bottlenecks and reduces noise, enabling faster, lower power, and more reliable quantum operations. Then what else we have? On-chip SFQ logic, minimize signal travel distance, cutting delay from microseconds to nanoseconds. Then by eliminating bulky cabling, SEEQC reduces thermal and electrical interference, ensuring cleaner qubit signals. Cryogenic digital logic runs at picowatt power levels, enabling sustainable scaling without massive overhead. I mean, that's also clear because we are working with superconductors. We don't have any electric loss due to currents running through the system because it runs at zero resistivity, and therefore you are not, let's say, in the microwatts or nanowatts, but in the picowatt of power consumption. I guess most of the power consumption happens because you're basically still creating electromagnetic fields that interfere with the environment, which might not be superconductive, and therefore creating some loss, as well as there has to be at some point an interface to some, let's say, classic electronics, which also creates some loss, I would assume. And then finally, modular chiplet architecture allows more qubits and control layers to be added seamlessly, supporting long-term growth. And that's the scalability approach, right? Take a closer look. So SEEQC's technology is built from the ground up to solve the biggest bottlenecks in quantum computing. Each layer of our system on a chip architecture is engineered to speed, precision, and scalability, from cryogenic processors that minimize heat and noise to integrated digital control that reduces complexity to modular scaling designed for enterprise class systems. Scroll through the features to see how SEEQC's innovation work together to deliver practical, energy efficient quantum computing. And here we have the, let's say, different stages. So it starts with the cryogenic SFQ processor. That's what we've seen before. Oh, that was too quick. So our single flux quantum processor operate at gigahertz speeds while producing negligible heat at cryogenic temperatures. That means control logic can live right next to the qubits, fast, efficient, and undisturbed. I'm too slow, that's why it keeps on rolling, probably. Let's see what else we have. Integrated qubit control readout. So read and reset qubits faster than ever. Our yellow release showed the world's first digital qubit readout and control at 20 millikelvin with reset times under 100 nanoseconds. Proved the scalable systems aren't theory, they're here. The next step is then the error correction and modular scaling, which in this case says digital integration enables real-time error decoding with far less overhead. Our modular design with multi-chip architectures and interposers lays the groundwork for scalable error-corrected quantum systems. And then finally, the third stage is the hardware spec snapshot. Here it says from gate speeds measured in picoseconds to energy per operation in picojoules. SEEQC specs speak for themselves. Probably the chip is as fast as this rotation system here, because I cannot really keep up with it. Compare our efficiency and performance against conventional systems, and the advantage is clear. Yeah, so this carousel here is very fast, I would say. And unfortunately, it's always moving. But there's a nice animation next to it, so don't want to be too negative here. So the SEEQC solution, an integrated and end-to-end solution for scalable quantum computing. So here, I guess we see some software interface as well on how to control this maybe, or how to run controls with it. So there's this browser, and there are also some graphs here that we can see going along with it. So DIGJI software and control. So SEEQC's DIGI software provides intelligent calibration, control, and system integration, and interfaces seamlessly with industry standard quantum software stacks while ensuring ultra-low level hardware access. And here we see basically the stack of it. So software and firmware embedded control, simplified system use, scalable qubit calibration, streamlined classical interfacing, roadmap to open up lower level controls for custom algorithm primitives, $4 million saved per system generation, and then enables fast development, lower internal R&D costs. Foundry capability, so they don't just design chips, they also build them. The superconducting chip foundry also allows rapid prototyping and proprietary process development. So we see that we really have a deep integration here. So it goes basically from designing the chip over designing the software of the chip all the way to manufacturing this chip in their own facilities. And then down here, there are also some roadmaps and milestones. So SEEQC's process is measured in proven milestones, not promises, from the first full system in 2022 to the world's first digital qubit control and on-chip readout. Each year has marked a clear step towards scalable quantum computing. With DARPA, IBM, and NVIDIA as partners, and over 100 patents secured, our roadmap shows a consistent path: larger systems, deeper integration, and fully cryogenic error correction. And here we have the roadmap. I will not go through all of these stages now. Just to show, so we are in 2026. There are various different items here. So we see for Q1 2026 digital XYZ driver for modular based system For Q2 2026, we see the multiplex digital XY and the multiplex digital Z readout. And then in the end of 2026, neural network pre-decoder for error correction. So we see they're moving also towards implementing error correction on the chip. For 2028, we then see here the next chip iteration, and here it says multiplex digital XY, multiplex digital Z, multiplex digital readout, and quantum error correction, all implemented on the cryogenic chip. We again see a link to the white paper, and that's everything about the technology. On the use cases side of things, very briefly, so adopted by leaders in quantum and AI. What do we have here? So where quantum meets real world. There's one case study with IBM, scaling with IBM, so quantum benchmarking phase B award, collaborating under DARPA's quantum benchmarking initiative to explore integrating SEEQC's SFQ chip-based control technology with IBM's quantum computer systems, 10 times cost advantage, on-chip readout and control, so chip scale multiplex readout and control electronics integrated with qubit chips, advancing IBM's roadmap to fault-tolerant quantum computing by 2029. So multiplex readout and control electronics all integrated into the qubit chip. And then billion-fold energy reduction. We've talked about that before. There's another case study here with NVIDIA. And I guess there are also some further stories down here about the industries that they are impacting. These are, I guess, the typical ones that we've seen before. Like logistics optimization, communication, energy, material design, material simulation. So basically what quantum computers might be useful for. Here's something on the financial backing. So since 2019, SEEQC has raised over $100 million to accelerate the path to scale quantum computing. We are supported by world-class investors including EQT Ventures, M Ventures, LG Technology Ventures, Blue Yard Capital, Merck, KGaA, and other committed to build the future, the quantum future. And then there's some notes here of the different people that are supporting and some basic explanation on qubits and quantum computers as well. Good. Let's quickly hop onto the foundry, because I think that's also interesting. So they're not only designing the chip, as mentioned before, they're also manufacturing it with a foundry. So while some need to go overseas for their chips, we walk across the street. And then, here's some information about the foundry. I will not go through the videos now, but let's see what the text says. So the SEEQC foundry is the premier commercial foundry of superconducting ICs and custom fabrications. It provides services to fabricate the world's most complex superconductor electronics and provides a unique capability to support the quantum computing R&D community. As part of SEEQC's Hypers legacy, the facility has fabricated more than 5,000 separate superconductive electronic chip designs. The foundry can produce virtually any superconductor chip for commercial, academic, and government markets, and offers design, development, simulation, layout, fabrication, cryogenic high-speed testing, and packaging in a world-class production environment. And I mean, this is very interesting. So 5,000 different designs, sounds like there's a lot of R&D, a lot of fast iteration happening there. I remember when I was in my PhD time, we went to visit the CIMMIT Institute in Shanghai, where they were also doing a lot of superconductor research, for example, to build SNSPDs, so single photon detectors based on superconductors. And they also had a testing, or let's say a lab facility where they were building these chips, basically like a foundry. So it really, to me, looked like a foundry. They had basically the spin coaters that you would normally use in a small foundry setup. So instead of, let's say, a typical research clean room where you are doing chip by chip based research, where you put a chip on the spin coater, then it rotates, it coats the chip, then you take it off, you put it in your box, you go to the next room, to the next step with it, reactive ion etching and so on. And always the chips are very, very like tiny test chips. At the CIMMIT, and probably also here at the SEEQC Foundry, they were operating not just on wafer, but like on batches of wafers. So they had these boxes where you have multiple of the wafers. So the chip is maybe like this, but the wafer is like this. So you can cut it later on and create many chips with those. And they were not just working on a wafer basis, but they had multiple wafers which were stored in like a storage box. And then you basically plug in the storage box to your production line. And then it automatically spin codes and does the lithography, and then you can do the development in the next machine. You can connect all of them with each other. So with robot arms, they basically transform or transport the wafers from one to the next station. And sometimes if the production line becomes too long, and that was back then at CIMIT the case, then at some point you have to have a second port where you take out the wafers again and then you put it in the next production line. So there's a manual step possibly in between. I guess it's very similar here. I don't know, we cannot see the foundry here. But you can see they also offer services. So you can request to have things manufactured there. Here it says a little bit about that. So our state-of-the-art 150 millimeter wafer processing capability supported with advanced equipment in manifold clean rooms. So 150 millimeter is the size of the wafer. There are different sizes. There are small ones. There are also very big wafers, depending on what type of technology you're working on, what technology node, what chip it is, right? The high volume capability allows customers to take advantage of rapid improvements in both yield and performance. We provide complex superconductor chip fabrication services to governments and leading businesses and academic organizations around the world. For a customer list and reference, please contact us. Then it says superconducting planarized multi-layer process. So standard process with multi-project wafers or dedicated wafers, applicable for Josephson junctions. So the very fundamental circuit elements of superconducting electronics, including SFQ, digital and mixed signal circuits, analog Josephson circuits, SQUIDs, etc. So SQUIDs is for superconducting quantum interference devices. So basically more or less sensors based on superconductors, magnetic field sensors. Then they have superconducting sensor process, so including TES and SNSPDs, that's the single photon detectors I talked about before, nanofabrication services, to incubate custom processes from startup to pre-production stage. Here we see a wafer prober, so probably they also have some way to test the quality of these produced samples, which for superconducting samples is maybe not as easy as for standard chips, because you also have to bring them to cryogenic temperatures to actually test whether they are really working the way they're supposed to work. And then there's also superconducting and non-superconducting multi-chip module process here as well. It says the niobium process, so I guess that's the material they are using, niobium. There are many different semiconductors. I think the first one discovered ever was mercury, back in Leiden, which I think back then the Nobel Prize was also accounted to. Niobium has some very interesting properties, so it's quite a stable superconductor. I think aluminum or aluminium, depending on where you come from, is also a very interesting material that people are using a lot nowadays in superconducting technology. When I was working still in the clean room, we also had niobium. I think it's maybe the class 1 superconductor with the highest critical magnetic field / critical temperature. But now there I'm not 100% sure. I'm not a superconductivity expert, but you can Google it, you will find it. So the SEEQC foundry features a complete niobium-based superconducting integrated circuit fabrication line. The niobium process has proven reliability as demonstrated by circuit operations through 7,000 thermal cycles without failure and no changes in device characteristics after 5 years of shelf life. And I guess that's different for I guess that's different for things like aluminum, where you have a native oxide layer forming and maybe also some further oxidization because of thermal cycles and other stuff ongoing. So here's the standard process. It says various different things about it. I'm not going to go through all of the details now. Then the interlayer dialect maybe like the dielectric material, which is PECVD, so plasma enhanced chemical vapor deposition, silicon dioxide, and low loss silicon nitride. Proven high volume production, demonstrated yield and reliability, use of SEEQC proprietary simulation tools and device models, optimized subcircuits, availability of standard subcircuits and layout primitives, flip chip bonding with superconducting and non-superconducting bumps. A lot of information in there. PCVD is a specific processing technology. I'm not going to go through that one now. There are other ones as well, like atomic layer deposition, ALD, to create oxides. Every single one of them comes with advantages and disadvantages. In Jülich, we had a lot of different ones where I was doing my PhD. We had the Helmholtz Nano facility, which is basically a place where you have so much of this process technology, you can try out various different ones. What is interesting here is also the flip chip bonding. So flip chip bonding is, so what is bonding? Let's say you have your silicon chip. Now you need to somehow connect it to the outside, right? You need to connect from the electrical circuits of the chip to the printed circuit board that you have. And usually the way that you do it is by connecting the chip to some housing, to some case of the chip, which is then called packaging. And the package then has like soldering bumps or soldering connections where it connects to the printed circuit board. One case of a CPU, you sometimes have like little pins down on the circuit board that connect to the CPU. Now let's think about this for a moment. How does it work? So usually the chip has some surface, and we put little fields, like little metallic fields on there, where we can then put a wire, a metallic wire, and then we connect it to the case where you have, let's say, the outside port that can be soldered to. And this is usually called wire bonding. There are different ways of doing that. You can use aluminum, you can use gold. There are different machines to do that. Now, this wire bonding really needs you to physically connect with a wire the chip to the outside. That works well if you don't have too many of those connections, but you can imagine if you have many of those connections, then at some point it becomes difficult to draw all of these little wires. Besides that, you also sometimes want to have chips interfacing with chips. So you could, for example, imagine a case where you want to create a magnetic field above your chip layer, and you could now take a separate chip which has a little coil printed on it with lithography, and then glue it on top of the other chip. And in order to connect those two chips electrically with each other, you can use something that is called flip chip bonding. So you basically take both chips, you put them together, and then you are like using some technique, some ultrasonic bonding technique to kind of glue them or melt them together in these specific connections. And these connections, they are then these bumps. And these bumps, they are available here in superconducting version and non-superconducting version. And that way you can connect chips to each other, which sometimes is important from a processing technology point of view. There are additional services here, just going through them, and then that's basically everything about the fab. Let's quickly round today's session off by scrolling through the about part of SEEQC. So what is their mission? It is to deliver scalable, energy-efficient quantum computing that will revolutionize how the world solves its hardest problems. SEEQC was founded to break the barriers preventing quantum computers from scaling. Our team of physicists and engineers combines decades of expertise in superconducting electronics to build the world's first quantum computer on a chip. Approach the quantum computing challenge differently, and then that's basically what they are up to. SEEQC is built upon the fundamental premise that to deliver a commercial, scalable, and cost-effective quantum computing solution, classical readout, control, error correction, and data processing functions must be integrated with a quantum processor. Just as the greatest advances in modern classical computing occurred with digital chip-scale integration of key functions, leading to a drastic reduction in system complexity, I/O count, and cost, the same will be required in quantum computing. We are developing a platform to deliver that integration. SEEQC is developing the first digital quantum computing system on a chip. SEEQC combines classical and quantum technologies to address the efficiency, stability, and cost issues endemic to quantum computing systems. SEEQC's quantum system is required to make quantum computing useful and bring the first commercially scalable problem-specific quantum computing applications to market. The company is one of the first companies to have built a superconductor multi-layer commercial chip foundry, and through this experience has the infrastructure in place for design, testing, and manufacturing of quantum-ready superconductors. SEEQC is a spin-out of Hypres, the world's leading developer for superconductor electronics. SEEQC's team of executives and scientists have deep expertise and experience in commercial superconductor computing solutions and quantum computing. SEEQC is based in Almsford in New York, with facilities in London, UK, and Naples, Italy. Here you can see the leadership. And you see, there are like different functions here available. Like you see that there's a finance, a CPO as well. So it's not only, let's say, the technical functions here, but like a proper setup for a company. There's an advisory board and a scientific board or scientific advisors. The investors and partners listed here as well. Organizations working with them. We've gone through a couple of them, both from the academic space, but also from the quantum space and the commercial space. And again, a call to action to join the team. With that, I think we are already at the end of today's video. I hope you liked it. If so, please make sure to give the video a like, especially if you made it all the way to the end. I'm looking forward to see you in the next one. Until then, bye-bye.